Hello everyone, my name is Ryan Schul. Welcome to my channel here. So today I want to talk about anomaly algorithms, and we're going to compare and contrast a few different anomaly algos. Okay, we're going to take a look at a broad range of well-defined core set of dedicated anomaly algorithms, right? Anomaly is an outlier, so anything that's unusual, different from the data set can be considered an anomaly. And it's not necessarily a super high point or a very low point. It's things that just don't match the regular general pattern of the um, the normal data set, or it can be called the baseline of the data set, right? So whatever is normal for the entire data set is defined as normal. Anything outside of that is an anomaly or an outlier. So we'll examine a few code templates and run them side by side and look at the performance of each one. So I did a quick Google search and I came up with this. I just Googled for, what is this over here? Scikit-learn anomaly detection. This is the first thing that I found. So comparing anomaly detection algorithms for outlier detection. That's what it's giving me here. So basically you'll see there's a handful of these. Okay, when this loads up, it's going a little bit slow here, you'll see that we find typically IsolationForest. This one is very common. There's a couple more that show up. LocalOutlierFactor, one class SVM. Oh, so support vector machine. If I go down a little bit over here, these are the four in the scikit-learn universe, right? So robust covariance, one class SVM, IsolationForest, LocalOutlierFactor. So I looked at three of these, okay? So I'm looking at LocalOutlierFactor, IsolationForest. This is my personal favorite right here, and one class SVM. I didn't even know about this other one until like a few minutes ago, so I didn't review this one. It's called robust covariance. I can see kind of how this one works. You can see how each algo kind of performs a little different from the others, right? This one, what is it called? Robust covariance. So it's looking for things that move together. Covariance is items moving together, and it's robust. So it's, I guess, more flexible in terms of how it captures or how it calculates its covariance. So these are moving together. You can see that this small concentration moves with this big cluster over here. And this right here, even though it has the same pattern as 2 and 3 and 4, they're sort of defined or categorized slightly different, right? So robust covariance wasn't really on my radar. I didn't even look at that. I've never even heard of that until about just a few minutes ago, but I reviewed these other three. So I think these three are the popular ones. And we can see, I've got my notes here, the pros and cons of each. So the idea of the IsolationForest is randomly partitioned feature space. The type is unsupervised. These are always unsupervised, okay? So supervised is when you know what the outcome is and you try to measure your predicted results against the holdout test results. Unsupervised, you know what the outcome is going to be. You just let the algorithm run wild and it tells you what you need to know. You don't tell it what it should know and how accurate it should try to make predictions compared to what the actual prediction would have been, right? This is unsupervised, so you don't know what the outcome is. The algorithm tells you what it is, okay? So the assumptions here, anomalies are different in different feature spaces, handles high dimensional data, non-parametric. So the second one I'm looking at is local outlier factor. The idea here is that points are in regions of significant lower local density. This is an outlier detection algorithm that I guess says novelty equals true. We'll see an example of that in just a minute here. The assumptions are normal points lie in dense regions. The pros and cons are right here. Good when anomalies are located sparsely rather than globally, and captures local structures. Cons, KNN-based, naive. So this is a naive sort of algorithm, right? It's not too smart, but it does a good job at what it's designed to do. Sensitive to neighbors and hard and high dimensional data spaces. The third one I'm looking at here is one class SVM, so support vector machine. The idea is to learn boundaries around the majority of the data and feature spaces via the support vector machine, so that's fine. Assumptions of normal data can be well enclosed, and kernel decision boundaries are made powerful with good kernels and can model complicated shapes. The cons are it doesn't really scale well with large N, It'll still work when it says it does scale well. It just means it takes a lot longer to run. So if you have a large number of n, 100 or so, it's going to take a long time to run. If you have a few n is the number of groups that you're looking for. If it's 4, 5, 6, 7, 8, 9, 10, probably going to run pretty quickly. If you have a lot of groups, it's probably going to run slow. Sensitive to the kernel choice. Okay, so that's where you begin, almost like a random choice where you begin upper left, upper right, lower left, lower right. So it's sensitive to things like that and needs careful scaling and tuning. Okay, so that is basically what we're going to look at here. We're going to compare and contrast these three types of algorithms and see how they shake out relative to their peers. Another part of this, almost like part two, I'm going to make a separate video. I'm going to validate the performance metrics of these anomaly algorithms next. Okay, so I'll swing back and make another video of that. So I'll show you in this video how to run these things, and next video I'll show you how to compare the performance of each, right? So if it's spitting out numbers and making generalizations and saying, okay, this is what I recommend, how do you compare that to other algorithms? Because if you just get the results and say, okay, this is it, this is done, that's fine, but how does that compare to other similar types of algorithms that you could have run? Could others outperform the one that you picked? That's what we're going to look at in the next step here. So let me go ahead and run the code, Control Enter to run the cell. Okay, and we are going to look at fraud data in this case. So I've got several videos on my channel about fraud data. Fraud is, you can imagine, anything from anti-money laundering to credit card fraud, right? Somebody using the card that it doesn't belong to, stolen ATM card, things like that, credit card fraud. Okay, so it's pretty broad, pretty deep, and pretty interesting too. And this is a big problem. Okay, this almost put PayPal out of business back in the day when they first opened their doors. There was all kinds of fraudulent transactions on the PayPal platform, and it was like whack-a-mole. Based on the news article that I read, I wasn't around, I wasn't there, so I don't know firsthand experience. But I guess they were being attacked just relentlessly by these fraudsters, and almost brought PayPal to its knees. But somehow it bounced back and fought off the fraudsters. Okay, so maybe they use this algorithm right here. I'm about to show you. I'm not sure, but this could help you immensely. Okay, so fraud is the name of the game here. We are going to go ahead and look at 24-hour period and a 7-day period, so different time frames, countries, and is this an international transaction or not? And the device that the fraud was committed with. Was this a cell phone? Was this an actual tangible credit card? Was it a laptop? Some type of smart device? It could be a couple different things, maybe even Apple Watch. I'm not sure, right? Fraudsters are very clever, very, very cunning. They can come up with all kinds of new tricks all the time. It's hard to stay ahead of these guys, but that's what we need to do, right? So we have the data frame here. We have a dictionary. You can tell by the curly braces here. And this is the key. This is the value, key on the left, value on the right, key on the left, value on the right. So we have the amount, the hour of the day, the 24-hour period in terms of numbers, average amount over the last 7 days. So we're looking at time series here. Country is international, and then device that the fraud was committed with. And we're going to go ahead and add some weights to this fraud, right? And look at the logarithmic changes of these different items in the data frame. So these are different features: the amount, the country, international, yes or no, device, and the number of transactions in the last 24 hours. Okay, we're going to take probability of fraud and set that to 1 divided by 1 plus the exponential of the log, right? So the exponent would go higher and higher, quicker and quicker, and the log would go lower and lower, slower and slower, right? So this would offset, the exponent would offset the log, right? And we're looking for the fraud rate. So here we have the data frame. The fraud rate in this case is 0.573. So about 5.7% of the time, close to 6% of the time, we actually have fraudulent transactions. It's not too much, right? As you would expect, most transactions are not going to be fraud. If that was, this company would go out of business very quickly. But you can't probably expect no fraud at all, or at least a fraud attempt, but you do want to try to prevent actual fraud and keep it as de minimis as possible, or as minimized as possible. And 5% to me sounds pretty huge. It sounds like there are some holes in the security of this company, there's some cyber threats here, or somebody is attacking or submitting some fraudulent activity on this platform, and somehow it's getting through at the rate of 5%. Again, seems pretty high. Um, so we have to investigate. We have to figure out what's going on. If the overall fraud is low, like if these transactions are $70, maybe $28, and this is fraud, maybe it's not super urgent to be concerned about this. Like if we're only losing a couple $100 per day and we're doing millions of transactions, okay, I understand we'll probably not get fraud transactions down to zero. There's probably always going to be some, at least a couple are going to sneak by, but if they're very small, we can probably live with it. And in this case, it's fraud. These are all zero frauds. So there's no fraud here to say for sure. If it's a bigger amount, I'd be much more concerned. If it's a smaller amount, I'd be less concerned. Again, hard to get this stuff down to zero, but that would be the goal, right? That's why these guys have jobs, because they're trying to be vigilant and always stay one step ahead of the fraudster. But in reality, the fraudster is one step ahead of you. Okay, so you have to be very innovative and very cunning, because if you're not, these guys are, and they're gonna figure it out. Okay, so we're gonna look at the columns here for our featured data set. Amount, the hour of the day. Again, we saw this before, is international. Whoops, I just copied and pasted accidentally. International and the device. So what I want to try to do is predict fraud. Is there fraud here? So the target column is going to be is fraud. That's what we're trying to predict. And the independent variables are over here, okay? So independent can be anything. Independent is independent by definition. It's independent of the dependent. The dependent variable is dependent by definition on the independent variable. So we're trying to predict, is this fraud? That's the dependent variable. That's going to be the y. Independent is going to be x. We set it up with this algorithm right here. First, we have to scale everything. So whenever you're dealing with data that is, oh geez, I just forgot the term. What was it? Non-trained data. Sorry, I'm gonna go back there. Oh, I just forgot the term. Oh my God, I'm so bad at this stuff now. I used to memorize this. I stopped memorizing things and just started focusing on solving problems and being uh, more problem solving, more forward thinking, to get away from all the memorization of things. So basically, yeah, basically this is it. Okay, so supervised. Anytime we're dealing with unsupervised data, which is IsolationForest, it's also local outlier factor and one class SVM. Any kind of anomaly detection algorithm is unsupervised. Any kind of clustering algorithm is unsupervised. Again, you're not telling the machine what to do. It tells you what to do. It's unsupervised. There's no guidelines to follow. There's no guardrails to stay within. With your supervised learning, like a regression problem or a classification problem, you have a known or expected outcome. You tell the computer, I want to match this, and it tries to match it and make predictions as accurate as possible. With unsupervised, there is no supervision. You let the machine run wild. It tells you what to do. You don't tell it what to do. So anytime you're dealing with unsupervised data, you will have some type of standard scaling. You have to take everything from a broad range of outputs or values or whatever and scale that either 0 to 1 or -1 to +1. Okay, it has to be in the same relative scale, and you're not taking something that's an outlier and converting it to a non-outlier. It's not like that, but you're just making everything on a relative same scale. Almost like, what's an example? Almost like if you have US standard system and metric system, you'd convert all to the same system. You wouldn't compare metric to US standard. It just doesn't make sense. Even though there's the same base underlying, the numbers are going to be very different. You want the same scale for everything, and then the unsupervised algorithm can go ahead and be trained and tested and fit and make accurate predictions. If it's not scaled, it's really bad practice. I mean, it'll still work and it'll still output something, but it could be anywhere from nonsense to like just kind of like weird output. You want to scale it anytime you're dealing with unsupervised. So any kind of classification or anomaly detection, scale the data. So just remember that rule. Okay, so fraud rate 5.73, fit anomaly detectors. We'll compare IsolationForest, local outlier factor, one class, SVM, and EllipticEnvelope. So was that over there before? No. See, okay, so there was 4. I was looking at 4. This robust covariance, I just learned about this literally today. So I guess it's similar to the others, similar but different, right? They all do um, have kind of this different methodologies, but we're going to look at these four. I'm not sure what the other one is. It just popped up for me. So maybe that um, deserves its own video. I'm not sure. I have to look into that a little bit. I just learned about this thing today. So we have isolation forest, number of estimators. I'm going to set at 200, confirmation fraud rate. That is just going to be a rough guess. I can't say what's fraud and what's not fraud. Again, this is unsupervised. The machine is going to tell me what to do. I can't tell it what to do, okay? It's going to tell me what to do. So I'm just going to say, go ahead and try to figure out fraud as best you can, because I don't know what fraud is. I can define it, but then I'm working with more of a classification type of problem or a regression type of problem. But this is unsupervised, remember? So it's an anomaly detection problem. You could probably use a clustering algorithm in lieu of an anomaly detection algorithm. They're designed for different purposes and the outcome is going to be different, but these two classes of algos are more similar than they are to regression or classification. That's just a different type of problem and return this off. So we have one class SVM. Again, we're going to scale all the data, and these are called hyperparameters. By the way, anything within the model parameters here are hyperparameters. These are all hyperparameters, right? So you can set that and train the model on that. These are optional. You don't have to set these. If you want to, great. If you don't want to, that's great too. It's probably going to help the learning and facilitate how fast the model converges and produces an output. So I would encourage you to look at these hyperparameters and try to figure it out and try to utilize those. It's going to work to your benefit. If you don't want to, it's still going to run. It's still going to spit out a result, but it might not be as accurate or as precise as you would expect. Okay, so I'm going to go ahead and run all four. Okay, and then I'm going to run a little loop for model and models and items. So these are all the models and all the items are these four. So EllipticEnvelope on class SVM, LocalOutlierFactor, and IsolationForest. And this is running right now. Let's see what the output is. Okay, I'm going to shut that down. I already showed you that one. Okay, so we're fitting the IsolationForest. This will take just a minute or so, probably less. It's going to fit each one. You have to train, test, and fit each one of these models. Then it spits out the results, and then we can interpret the results in just a minute. It might actually take a couple minutes. So I'll probably, I'll hit the pause button at this point, and I'll come back when this thing is done. Okay, so we have all four done. We can continue on. IsolationForest, LocalOutlierFactor, one class SVM, that's the support vector machine, and EllipticEnvelope. Okay, so we're all done training, testing, fitting the models. We can go ahead and see what kind of results we're getting. So the results are going to go into a list. I'm going to append everything to a list, and the scores of the data frame are going to go into another list. You can tell by the square brackets, this is a list. This is a different data type down here. You can tell right here by the evidence of the curly braces, this is a dictionary. So key value, key value, key value. Okay, and down here we have a data frame. These are the big three. There's also a tuple. Some people use tuples. I'm really not a big fan. I don't even know if I've used tuples more than 10 times in my entire life. Maybe once in a while. It's pretty rare. I think anything I need to do, I can accomplish with a list or a dictionary or a data frame. Tuples are okay. They actually come in curly braces like this with the kind of curved brace, not the squiggly braces. I don't like it that much. I just don't use it. So that's my personal preference. So we're going to take everything, put it into results and scores data frame. If I could do Control F, you can see it looks like this down here. Append temp. Temp comes from this dictionary. If I look for results, Control F, results go down here. So again, append, that can go into another dictionary, or you can just append it directly. So this goes from a dictionary into append. This is appended just directly into that, right? So it's kind of personal preference. Just pick the way you want to use it. I wouldn't say one is better than the other or one is worse. It's just different strokes for different folks. You do what you want to do. So we go ahead and use each model. The model comes from over here. So these are the models, 1, 2, 3, 4, for model and models. These are the models, right? So this can be anything. This could be Ryan. This variable right here, this could be I, it doesn't matter. The item that you iterate over can be named anything. It doesn't have to have a specific name, but this has to be the name of the items in the list that you're looping over. Or in this case, it's actually a dictionary because each thing is a key value pair. So we have the results data frame, the models. We are looking for the X test scaled. Remember, when it's unsupervised, everything is scaled. So any kind of anomaly detection algorithm or any type of clustering algorithm, you really, really, really should scale it. You don't have to, it'll still run, but it's going to probably produce some weird results unless somehow naturally the data set is already scaled, then you're fine, but most of the time it's not, so you have to force it to be scaled. And again, it goes from 0 to 1 or -1 to 1. You just take everything and condense it onto one sort of like baseline relative comparison um, measurement, right? So we're going to look at all the scores and look at the model. The ROC, AUC, this is area under the curve, and area under the curve, and then model. Is there fraud or no fraud? And then the model name again. So we take everything, flip it into this list, and everything is condensed nicely into this data frame when it runs, when it's all done. All right, you take everything as results, create a data frame. This becomes your data frame, and then we view the data frame. So in Python, guys, this is pretty super easy. I mean, really, it's called Pythonic. The language is kind of Pythonic. It's almost like the essence of the language or just the functionality of the language. Very streamlined, very simple. Sometimes in just a couple of lines, like just one line here, I create a data frame of all the results. If you go over here and look for results, you can see results come from here. Results.append, right, comes from the first list. And these are the scores. I just showed you this. The scores data frame comes from here. So we're taking all of the results, all of the scores, and appending everything just on one line. So it's super efficient. If you're in Visual Basic, VBA, C#, C++, C language, I never even had to learn C or C++, thankfully, because you have to deal with memory allocations and all these things. And if you don't get that right, the whole computer is going to blow up in your face. So with all these languages, my point is Python is probably one of the easiest to learn, maybe second to VBA. That's pretty easy. But it's pretty easy because everything is abstracted away. So all of the complexity of creating a data frame is reduced to one single line. All you have to do is put that pd.dataframe, encapsulate your data frame, whatever it is, a list, a dictionary, it can be a tuple. These are the different data types, convert that into a data frame, and then you have a nice, easy, modular version of the results in terms of columns and rows. These are the rows right here. It's actually rows comma columns, so the rows come first. These are the rows, these are the columns. Just easy to look at, easy to understand. Everything is structured. Everything is in one spot, so you can compare it easy to its neighbors. And we can see right here, the IsolationForest has an area under the curve of 0.84, and the PR AUC is 0.45. This one's 0.81, so slightly less. This is the local outlier factor. This one's a little bit less, one class SVM. This is a little bit higher AUC. This is about, no, these are about the same. This and that is about the same. This is pretty close. This one really underperforms the other two in terms of ROC and PR, but this elliptic envelope actually outperforms the IsolationForest and the local outlier factor, and it does so on both levels, right? The ROC, AUC, and the PR AUC. So let's go ahead and take a visual rendering, or it's called visualizing or visualization of the data itself. So I'm going to go ahead and plot that using Plotly. Plotly is pretty much my go-to plotting tool. I use this for almost everything. It's pretty easy to implement and to understand what's going on here. This is going to be a scatter plot, and I'm looking at FPR and TPR. Okay, and FPR is going to be the horizontal axis. This is the x-axis. The TPR is the y-axis. The mode is going to be lines. Okay, and you can go ahead and Google Plotly scatter plot, and you will find all kinds of documentation on this. It's pretty easy to learn and to get started on this. If you know it, that's fantastic. If you don't know it, I would encourage you to learn it. Plotly and scatter plot. I guess scatter plot. Okay, pick the first one here. It's going to give you a basic structure of what these scatter plots look like. And there's so many different versions of types of plots in Plotly. Okay, so here you have a basic scatter plot right here with just some random numbers. Here is an example of iris. This is a canonical data set here, very classic. You see this all the time in pandas and in Plotly too. So here's a great example. This is classic. Here's the data frame. X-axis is going to be sepal width. You just pop in whatever you want on the x-axis. Y-axis is sepal length. So the x is horizontal, y is vertical. Colors you can actually define as one of the fields in the data frame. The size can be another field, and the hover data is going to be the pop-up or the menu, the tooltip it's called, that comes up over the graph. So I would say go ahead and use these Plotly graphs. Dig in if you don't understand it. Try to learn whatever you can. You will learn a ton, and it's going to be very useful. It will serve you well for basically the balance of the rest of your career. So I have here all my x and y's. The x, again, is FPR. The y is TPR. So the x is going to be false positive rate. That's the FPR. TPR is the true positive rate. We want these graphs to go up, off, like straight up, and then over to the right as much as possible, as far away from the diagonal line as possible. So the further you are to the northwest quadrant, like right over here, the better off you're going to be. The closer you are to that, let me double click, the closer you are to this dotted line, this diagonal line, that is just a random guess, no machine learning whatsoever involved in this, right? So the further you are away from that dotted line, the better off the model is performing. You can see the elliptic curve at 0.902 performs the best. If I click on this, it disappears and reappears. If I click on the green, it disappears and reappears. Click on the red, same thing, disappear, reappear. Blue, disappear, reappear, okay? So clearly the elliptic envelope outperforms the others. This is anomaly algorithms compared. So in this case, the elliptic is the best, 0.902, and you can see that right up here. If you go back to the data frame, 0.902, one class SVM is the worst, 0.727. So that is rendered by the green dotted line up here, 728. It's just rounding up, and then 813 and 848. So local outlier factor is 813, IsolationForest 848, and you'll see that over here, 813, 848. It's rounding up. So IsolationForest is number 2. This is number 3. This is number 4, and this is easily number 1. Best performance of the 4. So we're looking at all 4 algorithms, comparing them side by side and seeing which one performs the best. And we have the final rendering down here in 2 ways. Number 1 with the elliptic envelope plotted in purple. So again, the more northwest it is, the better the model's performing. You want to be as far away from this dotted line as you can. The dotted line is just a random guess. Anything to the northwest of this is a more sophisticated model that is certainly going to outperform the dotted line. The dotted line is just making a random guess. You don't even need a computer for that, right? Just throw the dice or use your gut to make an instinct to make a guess. And you can see the elliptic envelope clearly outperforms IsolationForest, local outlier factor, and one class SVM as a box plot too. So the box plot shows the outliers. It shows you the mean, the median, and the mode. Over here, the mean, a little bit hard to read because it's all in red here. But I'm looking at the lower part is 1.05. The higher is 560, right? So up to 560 is the outer extreme. And basically, it's just capturing all of these outliers. So that's why this one performs the best in this given data set. So as best practice, if you really, really, really want to do this right and be very diligent, really should run all 4 of these, see which one outperforms the others, and pick the best performing algorithm, right? And it's always going to be different for every given data set. Whatever data set you have, really the best practice, I know it takes more work, it's more effort, more diligence, more dedication, more devotion, whatever you want to call it. Run all 4, but I set this up for you. You have all 4 here. You have all the you have the data frame, you have the key value pairs, you have the dictionaries and the lists doing the append and everything, so you can see how that works. So the best practice is to run all 4, see what performs the best on a given data set. And again, every data set is going to be different. Sometimes the IsolationForest will perform the best. Sometimes the local outlier factor will perform the best. Sometimes one class SVM is the best. In this case, elliptic envelope was the best. Evidenced by this, it's capturing all the data points, all the highs, all the lows, the max, min, the median, the mode, everything is captured right there. And by this purple line, we can see this is furthest away from the average dotted horizontal line, which is just a guess. You don't want to guess with these things. You want to use science, you want to use mathematics, you want to use proven statistics. that was invented centuries ago and has withstood the test of time, that's how you want to do it right, okay? So that is anomaly algorithms compared. I'm going to do another companion video with this, and this is going to be validation and performance metrics of anomaly algorithms. I'm going to do that next. I could do it together, but I'm going to split it up. I think really they do it justice. It really deserves two different videos. If I jam it into one, it's probably going to just get lost, you know, with in the confusion, and just kind of like I'll just deal with it separately, and I'll have these two companion videos go up together. So I'll post this a little bit later today. This is done. I will save this right here. I'll save a recent copy, and I will go ahead. Okay, save now. Good. I'll go ahead and save and export as an HTML file. I'll share all the code with you, so you have everything. I share all the code with all of these videos. I'm up to about, I think, 460 or close to 460 at this point. Every single one I created the code for, debugged it, tested it, and then shared all the code with everyone. So everything that I've done with a video always has the source code that goes with it. Okay, so I'll share that with you when I post this later today. I'm going to turn off the recorder, switch over to the validation and performance of these anomaly algos, and I'll do these two a little bit later today. So keep an eye out for it, and you'll see that drop in pretty soon. Okay, thanks for your time, and yeah, I'll see you in the next video. Bye.